on calcifiers. And so one of the biggest problems in today's world is climate change, and it's pretty common knowledge that this climate change is caused by increasing levels of CO2. And this graph depicts the monthly levels of CO2 in the atmosphere since 1955. As you can see, it's increasing at a pretty alarming rate, and this is due to the increasing burning of fossil fuels on our part. And so as this CO2 rises, as I said, most of us probably are aware that it's causing things such as climate change, which is associated with global warming and topics like that. But most people aren't aware that this high CO2 in the atmosphere is also contributing to ocean acidification.
Ocean acidification is when carbon from the air is absorbed by the ocean. When it is in the water, it bonds with water molecules to form carbonic acid, which increases hydrogen ions and decreases calcium carbonate and causes a decrease in pH in the ocean. Also, the decrease in calcium carbonate, we believe, would have a negative impact on calcifiers, which are organisms with a hard shell, because calcium carbonate is what they make their shells out of.
So to put that in perspective, 30% of the atmosphere's carbon is absorbed by the ocean daily, and that's 22 million tons. So we heard about this phenomenon and we were just fascinated by it, so we wanted to look at it, delve into it further, and look at it in our area. So we developed our research topic and hypothesis. Increasing acidity in the ocean will lead to decreasing calcification rates in calcifying organisms and a decrease in the amount of phytoplankton consumed. So how did we go about this? We went down to Recompense Shore, a 15-minute walk away from the farmhouse, and collected our specimens. We got 8 Mytilus edulis, or blue mussels, 8 Nucella lapillus, or dogwelks, and 8 Crustaceae virginica, or oysters. When we first got down to the beach, we felt that we had found the beach setting a world record for the least amount of mussels because we just could not find any. But after some searching and some lifting of seaweed, we found all our specimens and brought them back to the lab.
We chose to experiment on mussels and oysters because both are commercially important. And we chose dogwelks because they are a keystone predator, which means that the ecosystem that they live in would be affected drastically if there were none of them, and it's dependent on their existence to be a stable ecosystem. So we set up 8 different tanks, and in 4 of them we added carbon to decrease the pH, and in 4 of them we did not add carbon. And so we put 4 of each of the organisms that we collected into one tank from the one control tank with a higher pH, which would be lower acidity, and one in the experimental, or 4 in the experimental tank, which has a lower pH. We also had 2 tanks with only phytoplankton so that we could measure the feeding rate of the mussels and oysters. This is our experiment after we set it up. And as you can see, the ones that are on the slightly higher side of the table are the tanks with a higher pH, so they were less acidic. And the 3 tanks, there were 4, but one of them got cut out of the picture. On the side of the table closer to me were the tanks with a lower pH, and those are the ones that have the tubes going into them.
And so to initiate this acidic environment for our experimental tanks, we used a yeast process. And the yeast process is seen throughout the jars on the table. And what happens is the yeast would feed on sugar, which we provided for them, and it would start to respire, which means that it releases CO2 into the jars. And as the CO2 builds up in those jars, it would travel through the tubes into the connected tanks, which are the experimental tanks. And then as the CO2 builds up within the water of those tanks, it would cause the acidity to rise.
So every 2 days, we measured the density of the shells, the mass and the density of the shells of our organisms to see how the different pH levels were affecting them. So to measure the density, we used the buoyancy method. So we put a set amount of water into a graduate cylinder and dropped the organisms into the water one at a time. And because of the amount of space that the shell takes up, it causes the water to move and displaces it. So we could tell how dense the shell was by how much water it displaced. And we got accurate results on this because the bodies of mussels and oysters are neutrally buoyant, which means they are about the same density as the water. So they do not displace any water. So we could get a measurement of only the shells. And we also measured the mass balance every 2 days.
And so throughout our experiment, we recorded the pH in each of the tanks every other day just to see what was going on and if the experimental tanks were getting more acidic as we intended them to. And these were the results that we were expecting to see through all of the tanks, or that we were hoping that we would see. Because as you can see, the control tanks, which are shown in blue, and the experimental tanks shown in red, in both the dogwells and the phytoplankton, there's a clear correlation between them. So you can tell that the control tanks were in generally a higher pH than the experimental tanks were, which is what we were hoping, because we did want the organisms in the experimental tanks to be exposed to higher levels of acidity to initiate ocean acidification.
So although that was what we were expecting to see, this is what we ended up seeing in both the mussels and oyster tanks. In the experimental tank, in both of them, started off at a lower pH, being more acidic, but then throughout the experiment, it ended up raising and actually surpassed the control tanks, becoming more basic. Although this is not what we were expecting to see, we can still conclude, or we can still say that the experimental tanks the control tanks never had as low a low of a pH as the experimental tanks. And one of our hypotheses for why this could be is that water left out over time, its pH rises and it becomes more basic. So that could be one reason. And another reason was that both these tanks had phytoplankton in them. And phytoplankton are photosynthesizers, and they breathe, unlike how we breathe out CO2, they breathe in CO2, so that they could have been taking away the carbon that we were adding.
And throughout the experiment, we also tracked the buoyancy in each of our organisms throughout the tanks. And to do this, as Emily said, we used the water displacement method. And the y-axis on this graph measures the change in water displacement of our organisms. So for example, the underneath 0 means that there was a decrease in the average displacement of the organisms per tank. And above 0 means that there was an increase in the water displacement. And so throughout the experiment of 9 days, we see that the control tank stays pretty close to 0, which is what we were hoping for, because we were trying to initiate a very normal environment for them to live in. And towards the end of the experiment, the experimental tanks saw a great decrease of nearly -6, or lost nearly 6 milliliters in the water displacement method, which showed that they were not calcifying as much as the organisms in the control tank due to the higher acidity.
Over the course of our experiment, we had 5 mussels die. And yeah, our experiment was only 9 days, so that was quite a lot. So on day 3, one mussel from our experimental tank died, and that was the first muscle to go. By the end of the experiment, our entire experimental tank was dead. And we'd only lost one muscle from our control tank, though, which was on the very last day.
So clearly the muscles in the experimental tank did not fare as well as those in the control tank, which supports our hypothesis that this rising acidity will negatively impact their species.
Along with calcification rate, we also tracked feeding rate, and so we did 2 phytoplankton additions, one on the first day and one on the 5th day. And this is the data between the 1st and 5th day and how the phytoplankton decreased. And this you can see in the control tank, it decreased by over 3,000 phytoplankton cells per mil, while in the experimental tank it only decreased by 2,000 cells per mil. So we can state that, so the mussels in the experimental tank ate less than the ones in the control tank, and therefore we can state that the acidity negatively impacted the feeding rate.
During the second half of our experiment, when we were going to measure the feeding rate again, we accidentally got some sort of zooplankton into our experiment, and we haven't identified the species, but we don't have data from that second half since it was likely eating the phytoplankton too.
We also did this in oysters, but we found the data inconclusive and decided not to include it.
And this is a graph, much like the one shown earlier, of change in muscle buoyancy, but now representing oysters. And the y-axis works the same, measuring change in displacement. And the graph is very similar to the mussel graph in the way that the experimental tank decreases greatly in the average amount of water displacement by the end of the experiment. And one thing that we would like to point out is that on days 1 to 3 in the experimental tank, there it shows a spike of 6 added milliliters to the water displacement method, and we believe this is due to a calculation error because it's unlikely that within the first 3 days that the organisms were in the tanks, they increased their density by that much.
The data for the dog whelk buoyancy showed a lot of variation over the days that we measured. So we can't really conclude on what impact acidity has on dog whelk. And we believe that our inconclusive data might be because of the fact that dog whelks have denser bodies than mussels and oysters. So we may have, when we used the buoyancy method to measure their shells, we may have also been measuring their bodies as well. We were also going to do feeding rate for the dog whelks, but they never ate anything that
So why is this important? Why does this matter? What's the difference in a few dead mussels or some skinnier oysters?
The increasing acidity of the ocean is actually very important because it can lead to decreases in calcification of calcifying organisms, as was shown on the graphs of mussels and oyster density. And it can also lead to a decrease in feeding rate, which we saw in the mussels as well.
if there's a decrease in calcification and the shells of these organisms are less dense, they're not as strong, then it's a lot easier for organisms that would eat these organisms to get through the shells to their bodies inside, which they can eat. And also, they would have to use more energy for calcification, which would divert energy from reproduction. And they would also not have as much energy in the first place if their feeding rate was going down. So that could negatively impact the population.
And that would lead to, with dogwalks being a keystone predator, it could lead to ecosystem instability. And also, mussels and oysters are both part of a huge industry. The oyster industry is worth over $1.75 million in Maine alone and over $3 billion across the world. Along with mussels being such an economic worth, they also are just so abundant that the iconic rocky intertidal Maine beaches we all know so well would never be the same.
And throughout the course of the experiment, we definitely learned a lot, but I think one of the most important things we learned was how to work together as a group and how to incorporate all of our ideas and opinions into our final presentations and research papers.
This was definitely a challenge for us, being three somewhat perfectionists and in some cases overachievers. It was hard for the three of us not to have full control of everything going on. I think we all learned each other's strengths and weaknesses and ended up working really well together.
It was also the first time for all of us coming up with designing and setting up our own experiment of this large scale. So it was definitely a new experience, but we learned a lot from it.
We also learned how to make sense out of raw data and make graphs with Excel and do all these things, science in such a high scale that none of us had ever done before.
And lastly, we learned that through our experiment, there was many things that didn't go quite the way we expected them to. And so we can conclude that science can lead to unexpected discoveries that can then lead to further questions that we would love to research in the future.
And lastly, on behalf of all of semester 12, thank you to Carrie for everything she's done with us through that whole process.
Any questions for this group? Yes.
Could you guys speak to what your inspiration was for choosing this as a topic?
Yeah, me and Kitty, while we were on our coastal expedition, got a reading packet, as everybody got reading packets, but we were split up into groups, and part of our group was to study ocean's acidification effect on coral. And so we were both really interested in that, and we decided to do this experiment on oysters and mussels to bring it closer to home.
Other questions? Yes.
So how can you tell when you're feeding these little guys that they're not dying from, the phytoplankton aren't dying from the acidification?
Well, we had two different tanks with the phytoplankton, and one was just like we had two different tanks of the mussels. And so in one of the mussel tanks and one of the phytoplankton tanks, we were adding more carbon so that the acidity would be the same in those two tanks. And so then we measured the amount of phytoplankton in the more acidic tank. And then to find the feeding rate of the mussels in the more acidic tank, we measured the phytoplankton in the mussel tank. And then we found how much less phytoplankton there was in that tank. And then we did the same thing with the control tank with the higher pH.
Any other questions? All right, well with that, we conclude the semester 12 marine science presentations. Thanks.